At first glance, a distant exoplanet is only a pinprick of light. It is too small to photograph as a world, too faint to separate from its star, and unimaginably far away. Yet with a carefully timed observation, astronomers can read a chemical fingerprint from that tiny signal and begin to ask one of science's oldest questions: what are other worlds made of? This is the story of how the James Webb Space Telescope studies exoplanet atmospheres, not by taking a simple picture, but by measuring the subtle way an atmosphere changes starlight. The method is delicate, the data are limited, and every exciting claim must survive a long chain of tests. But the result is extraordinary. Chemistry, weather, and the history of planets can be inferred across interstellar distances. Imagine a planet passing directly between us and its star. The event is called a transit. Most of the star's light still reaches the telescope, but a tiny fraction travels through the planet's atmosphere first. Molecules in that atmosphere absorb particular colors, or wavelengths, of light. By comparing the star's light during transit with its light before and after, researchers can look for those missing wavelengths. The signal is incredibly small. A planet may block only a fraction of 1% of its star's light, while the atmospheric signature is smaller still. Telescope vibrations, detector behavior, stellar activity, and even drifting clouds of dust can imitate a planetary feature. Exoplanet spectroscopy is therefore less like taking a snapshot and more like hearing a whisper inside a crowded room. Webb is powerful because it observes infrared light, where many important molecules leave distinctive signatures. Water vapor, carbon dioxide, methane, and carbon monoxide each interact with light in their own ways. No single absorption line is a magical answer. Instead, scientists compare the full pattern with thousands of atmospheric models and ask which combinations remain plausible after every uncertainty is included. The first target is often a hot gas giant. These planets orbit extremely close to their stars, completing a year in days rather than months or decades. Their atmospheres are swollen by intense heat, making the spectral signal easier to detect. They are not comfortable places. Some may have iron and silicate clouds, but they are natural laboratories for testing the physics of planetary atmospheres. As a hot planet circles its star, one side may face the star permanently. The day side can be scorched, while the night side remains comparatively dark. Winds try to redistribute the heat, and the atmosphere becomes a moving engine of chemistry. During a transit we sample the thin boundary around the planet. During an eclipse, when the planet slips behind its star, we can isolate the planet's own glow and estimate the temperature of its dayside. That difference matters. Transmission spectroscopy asks, what does starlight encounter at the edge? Emission spectroscopy asks, how does the planet itself radiate? Together, the two views can reveal whether an atmosphere is clear or cloudy, whether heat is moving efficiently, and whether chemical reactions are being driven by sunlight. Clouds are one of the great complications. A high-altitude haze can hide deeper layers, flattening the expected molecular features. A flat spectrum does not necessarily mean an atmosphere is empty. It may mean that the telescope is seeing an opaque cloud deck, or that the atmosphere has been stripped down to a high molecular weight gas. This is why one observation is rarely enough. Astronomers repeat transits, combine several instruments, and compare independent reduction methods. They test whether a proposed molecule improves the model significantly, rather than simply choosing the most dramatic interpretation. In modern astronomy, confidence often comes not from one spectacular graph, but from agreement between many modest measurements. The star itself must also be understood. Stars are not perfectly steady lamps. Dark spots, bright regions, flares, and rotating magnetic patterns can alter the spectrum. For a small rocky planet, the star's changing surface may produce a signal larger than the atmosphere researchers are trying to measure. A planetary atmosphere can be discovered only after the star's behavior is modeled with equal care. Rocky planets are the harder frontier. Their atmospheres are thin compared with those of gas giants, and their host stars are often active red dwarfs. A planet in the temperate zone may receive the right amount of energy for liquid water in principle, yet still face intense stellar flares. Whether it retains an atmosphere depends on gravity, magnetic protection, volcanic replenishment, ultraviolet radiation, and the planet's entire geological history. Even water vapor must be interpreted carefully. Detecting water is not the same as detecting oceans, and detecting a molecule is not proof of life. Water can exist in a hot, dry atmosphere. Methane can be produced by biology, but it can also emerge from geology. Oxygen can accumulate through non-living chemical pathways. The scientific challenge is to identify combinations of gases that are difficult to maintain without a continuing source, and then to eliminate every plausible abiotic explanation. This cautious approach does not make the search less exciting. It makes it more meaningful. A possible biosignature is not a headline conclusion, it is an invitation to observe again, use a different wavelength range, study the host star, and build better models of climate and chemistry. Webb also gives us a way to study planets as historical records. An atmosphere is not just a blanket around a world. It is an archive of impacts, oceans, volcanoes, radiation, and escape to space. Two planets that formed from similar material can end up radically different if one loses its atmosphere early or if its oceans are locked into minerals below the surface. Look at the solar system and the lesson is obvious. Venus has a crushing carbon dioxide atmosphere and a runaway greenhouse climate. Mars is cold and thin-aired, carrying evidence that its ancient environment was more active than the barren planet we see today. Earth's atmosphere is the outcome of geology, life, sunlight, and time interacting over billions of years. When Webb examines a planet around another star, it is not merely cataloging exotic ingredients. It is comparing alternate versions of planetary evolution. A spectrum can suggest that a world is inflated by heat, wrapped in clouds, losing gas to space, or chemically out of equilibrium. Each clue narrows the story, even when the final answer remains uncertain. The telescope's most important discoveries may come from unexpected targets. A world initially selected because it was easy to observe might reveal unusual chemistry. A planet thought to be cloudless may turn out to have complex circulation. A small world may teach researchers that current models of atmospheric escape are incomplete. Scientific instruments are built to test predictions, but nature is under no obligation to follow them. There is also a human dimension to the measurement. The photons collected by Webb may have left their star years, decades, or centuries ago. They cross the void, pass through an atmosphere on a world we cannot visit, and arrive at a segmented mirror in space. From that faint arrival, a global community of scientists reconstructs temperatures and molecules using mathematics, laboratory data, and physical intuition. Every step is vulnerable to error, yet the method is powerful because the laws of light are universal. The same quantum transitions that identify water vapor in a laboratory can reveal water vapor around a distant planet. The scale is cosmic, but the evidence is built from repeatable physics. What happens next? Future observatories will extend these measurements to smaller, cooler, and more Earth-like planets. Better instruments will suppress starlight, increase spectral precision, and measure atmospheres over many seasons. The goal is not simply to find a second Earth. It is to understand how common Earth-like conditions are, how long they last, and which chemical clues deserve our closest attention. Perhaps the greatest surprise will be how diverse living possibilities can be. Perhaps the data will show that temperate, stable atmospheres are rare. Or perhaps they will reveal that planets can remain habitable through pathways no one has yet imagined. Either outcome changes our place in the universe. There is a practical rhythm to this work. First comes target selection, a bright star, a favorable planetary orbit, and a transit long enough to observe. Then comes calibration, in which the instrument's response is mapped using reference stars and internal measurements. Only after those steps can the faint difference between in-transit and out-of-transit light be treated as evidence rather than an instrumental artifact. Researchers also share the raw observations so that other teams can reproduce the analysis. Different pipelines may handle detector noise or stellar variability in slightly different ways. When several approaches reach the same conclusion, confidence grows. When they disagree, that disagreement is useful because it exposes which assumptions still control the result. A planet's orbit adds another layer of information. If the transit repeats at regular intervals, its year can be measured. The depth of the transit estimates the planet's size compared with its star, while the duration and shape can reveal orbital geometry. When these clues are combined with the star's temperature and size, astronomers can estimate how much energy reaches the planet. But equilibrium temperature is only a starting point. A real climate depends on reflectivity, atmospheric circulation, chemistry, and the ability of clouds to trap or scatter energy. Two worlds receiving the same stellar energy can therefore have completely different surface conditions. The atmosphere is the bridge between orbital mechanics and climate. Some planets may have atmospheres that are actively escaping. Extreme ultraviolet light can heat the upper atmosphere until the gas expands and flows away. Light elements escape most easily, potentially transforming a once thick envelope into a thin remnant. The resulting chemical pattern can preserve a record of how a planet changed after its formation. Other worlds may be renewed from below. Volcanism can release water, carbon dioxide, sulfur compounds, and other gases. Minerals can absorb and later release carbon. Oceans can transport material between the atmosphere, crust, and seafloor. A spectrum is therefore a snapshot of a planetary system in motion, not a permanent label attached to a world. The deepest lesson is that habitability is not a single switch. It is a relationship among a planet, its star, and its environment. A world outside a simple habitable zone diagram might remain interesting if it has tidal heating or a subsurface ocean. A world inside that zone might be sterile if it loses its atmosphere or becomes locked into a hostile climate. For now, the distant worlds remain points of light. But hidden inside those points are patterns, the fingerprint of a cloud, the warmth of a dayside, the residue of ancient oceans, and the chemistry of a planet under another sun. Webb cannot carry us across the interstellar gulf. It can do something almost as profound, let the universe speak through light. And when that light reaches us, the question is no longer whether a world can be seen. The question is what story its atmosphere has been telling all along.